Okay. All right. Okay. So I start now. All right, ladies and gentlemen, faculty members, honored guests, Mr. Carl Gomez in the house, and my dear students, I am delighted to introduce to all the participants today to our esteemed guest, Mr. Carl Gomez, who joined us today as a distinguished speaker in the global classroom heat transfer subject. Mr. Gomez currently residing in US, and now it's about around 1 midnight. Okay, AM midnight. And he is here today to share his knowledge and experience on the designing of heat exchanger using TMA TMA specification. We are here in UMP, are very fortunate to have Mr. Gomez once again. Previously, he graced our institution in 2016, I think, as a guest speaker in Master Program Process Plan Operation, and conducted a few training in UMP. Mr. Carl Gomez was a senior technical engineering professional and senior managing director at KLM Technology Group, United States. He has exceptional expertise and vast experience in engineering field, specifically in petrochemical and oil and gas industries. He is a certified practicing engineer, certified practicing project manager, certified practicing safety professional that are responsible to maintain high standard of professionalism and expertise in related competency area. He also accomplished author, editor, and contributor to many technical publications, including a renowned Commerce Handbook of Process Equipment Design. This handbook has been one of the main references used in Master Program Process Plant Operation in UMP on the subject of chemical process design and equipment. Until today, with publication, dedication to share the knowledge, advising the engineering practices, Mr. Gomez has been reliable source of information and inspiration to all engineers worldwide. Just Google his name, you will see many publication and contribution. Mr. Gomez worked on the engineering area. And today we have very privileged and welcome to Mr. Gomez back to our university as a speaker. Therefore, I would like to urge all of you to take advantage of this opportunity to learn from Mr. Gomez, experience and engage with the discussion during Q&A session after this. Very warm welcome to Mr. Gomez. Thank you again for your support. And the floor is yours, we can start. Thank you, Mr. Gomez, for your time.
Thank you for your kind words. And then thanks for the opportunity today to speak to you and so currently we have about 75 online. I don't think the chat box may not be working. The Q&A is working. The Q&A, I had one question about, we're recording this, would it be online? Yes, we have a YouTube channel, Carl Gomez. I have a YouTube channel and this will be posted on our YouTube channel. Give me 3 or 4 days to work on it, but we will post this on our YouTube channel. So thanks today for the opportunity. What are we going to talk about? We're going to talk about thanks to the university, KLM intro, building operational excellence, general heat exchanger design, heat exchanger design for clean service, for fouling service, and some troubleshooting. If I have time, I'm going to run through the troubleshooting. If not, we may skip that part, and then a Q&A. And so we can go from there. All right. Obviously, we want to thank the university to speak to your students and other engineers in this global classroom. We have 78 online right now. UMP is a highly rated university in Malaysia. If you wish to study or continuing your studies, we believe UPM is a great place for you or your children. I'm a retired engineer. I can live anywhere I choose to live. And I choose to live in Florida in the US, and I choose to live in Malaysia. I actually have an office in Johor Bahru. And so I think Malaysia is a great place to study and a great place to live, no matter where you are in the world. UPM should be considered for you or your children to continue your studies. So we're thankful to UMP. KLM, based in the U.S. since 1995, technical consultancy group, providing specialized services and equipment to improve process plant operational efficiency, profitability, and safety. We do training like we're doing today, engineering design guidelines, which we're going to talk about, process studies, HAZOPs, basic designs. We are helping a group in Johor that builds random packing and structured packing. So there's actually process equipment being built in Johor. And so I'm actually assisting them some in some of the marketing. We have a magazine, Engineering Practice Magazine, and we do other things. So here's some classes that we teach. Engineering design guidelines. We've developed 120 of them since 2007. If you've searched anything on the web, you found the engineering design guidelines. They look like this. I think your university is using them to teach, and about 4 or 5 universities in Indonesia are also using the engineering design guidelines to teach their students. So it's been well received all over the world, and we're thankful for the goal of the guideline is to take your engineering fundamentals and practically build a process data sheet. And we'll talk about process data sheets today. And that's one of the engineering deliverables that you have to do if you're designing a heat exchanger. If you're designing a heat exchanger, you're going to have to build a process data sheet. If you're designing a tower, if you're designing a pump, anything you design, you have to build a process data sheet. And these guidelines really are how to help you build a process data sheet. Like she said, if you've searched anything on the web, you found us. This is ResearchGate, and this is this week's. ResearchGate is an independent group where you can publish your documentation. So far, we've had 532,000 views on ResearchGate. And so thanks to you and your students and other students, the engineering and our publications have been well received. The heat exchanger, we have a chapter on heat exchangers, and it's had 3,000 plus views. And the Google Scholar, I'm probably not as good on Google Scholar as some of your professors, but we've got a few citations out there. And we have 26,000 followers on LinkedIn, and every time we post something, we get 4,000 to 8,000 views. Here was a post where we talked about process system troubleshooting, which was one of the chapters in the handbook, got 31,000 views. Here's a post where we talked about a chapter on process plant layout that got 42,000 views. So we've been publishing articles on the web since 2002, the last 21 years. Even if you estimate we only had 50,000 per year, this is still 1 million views. Our writings, since 2002, our writings should be in the top group of the most read engineering authors. Thanks for your support in making this possible. So the website's maybe 1,000 views, ResearchGate's 500,000, LinkedIn's probably 200,000 published articles. I've got about 15 published articles out there, and maybe 1.7 million views since 2002. And we're thankful that thanks for your support and other people's support in making this possible. So we began writing the College Handbook of Process Equipment in 2007. A young engineer was working for me, and every time he had a question, I'd go into my library and I'd pull him out an answer. And he said, well, you've got this great library. You need to go start publishing how to do things. So we started. And so it's been very well received. And I'd get emails from students asking for student discounts. The handbook is mostly purchased by companies, so the cost was high for students. So in June of 2014, we developed an idea to start an engineering association, utilize the handbook to train and certify individuals at a student rate, very low rate. We're now in the 9th year of association. We have over 2,000 members worldwide. And so it's hard to talk to the students to join after they go out and they get their first job. They realize, hey, I need to know how to build a process data sheet. And then they come and join. In April 2015, we started Engineering Practice Magazine, and the first issue, we're now in our 8th year. We've got great authors. and readership is approaching 10,000 issues. So we're honored and pleased that Engineering Practice Magazine is doing so well. If you want your articles read, you should consider publishing in Engineering Practice Magazine. And that's kind of who we are, a little bit about what we do. So let's talk briefly, some safety, just some introduction to the process industry. I want to talk briefly about that. There's at least 5 parts to operational excellence. A partial list might include health, safety, and environment, reliability, continuity of operations, quality, cost, and development. Safety, HSE is the number 1 concern. No project or operation can be classified as sustainable, optimized, or excellent unless it's done safely, while minimizing environmental impact. We've made great improvements in the HSE in the last 50 years. But because we started from such very poor performance, multiple deaths, multiple instances, we started so very poorly that we think we've done well. We started from maybe an F failing grade to maybe an average C grade. Because we have done well. We've gone from an F to a C, but there's still great opportunities for improvement. Let's don't be happy with a C student. Let's continue to improve our efforts for health, safety, and the environment. Reliability, a stable, reliable plant is the largest source of revenue. Reliable plant will generate far more revenue than a plant with multiple outages. You should develop a team to review equipment design, operation, and improve reliability. Teams should look for the low-hanging fruit first. Often a few bad actors reduce the reliability of the whole plant. You should calculate the cost of unreliable and of unavailable equipment. It's much, much larger than you think. Best performing plants have greater than 97% online. Many plants have less than 90%. For a large processing plant, this lost opportunity is $10 million a year. If you're an engineer, you need to focus on things that'll make $1 million a year. And it's easy to do, they're out there. Bringing this availability of your plant up 3 or 4% is around $1 million. So make sure you're looking at big ticket items if you're an engineer. Quality is reflective of internal and external aspects. External, well, I can sell my products better. Internal, if I've got to rerun products, there's an additional energy debit, okay? Most companies have quality audits for the sole purpose of receiving quality certification. Certainly a good reason. But wouldn't a better reason be to actually improve the quality? A lot of times the companies, they just want the they just do a quality audit for the certification. Most audit findings are above 90% compliance. Amazing and not true. They're going through the motions of an audit. A good audit team, I can walk into any processing facility and find 20 non-conforming quality issues. Okay, if you run a good audit, you're going to find some issues. If you're doing it just to get the paper on the wall, you're not actually improving quality. I was on a PSM audit. Previous auditor, every 3 years, you got to do a process safety management audit. Previous audit found 4 non-compliant issues. We found 37. The problem is the upper management will not be happy with finding non-conformance issues because they must deal with them. I've never understood this because it makes the plant more profitable if it's quality, and it makes it safer if it's a PSM audit. Cost control is particularly important. The 2 largest costs are feedstock and energy, all right? And if you can improve your feedstock utilization, it's $1 million a year for most plants. If you can improve your energy, it's $1 million a year for most plants, all right? Energy should be tracked. The industry standard for major companies is that energy is reduced 1 to 3% per year. The top tier performing companies reduce energy 1 to 3% per year. Most plants have the same energy performance or they're declining. Okay, while the best plants see yearly increases. And how can they do that? Well, they do equipment design, they do plant reliability. If you're on plants online, you're going to use a whole lot less energy. Motor power factors, pump efficiencies, lighting, equipment installation, heat exchangers, which we're going to talk about today, distillation, boilers, and heaters. this is a week course right here, just to talk about each one of them items and how we can do energy. And there's the current buzzwords of sustainability and so if we could just use less energy and be much more sustainable. If your energy cost is increasing, you need to put together an energy reduction team. All right. Each time you replace a piece of equipment, you should improve the energy efficiency of that piece of equipment. For a heat exchanger, if it's designed well, I can improve the efficiency. We're going to talk about this today, 3 to 5%. This is how the industry gains 1 to 3% of your improvements, by upgrading the equipment. You should not replace in kind. You should replace with a higher piece of equipment, higher efficiency piece of equipment. People development. The success of every company depends on the employee's understanding of the key business components. Employee training and development will unlock the company's profitability and reliability. All these 4 things we just talked about. The people have to break open them keys. People development. In process plant, the 2 largest failure modes are operator error and instrumentation. If I was a plant manager, I would have a large training budget and a large instrumentation budget, so I could get a bigger yearly bonus. Go after the low hanging fruit first. All right, so let's jump into heat exchangers. There are many types of heat exchangers. Heat exchanger fluids, gas, liquid. They can flow in parallel, they can flow counter current, they can flow in opposite directions, they can flow cross flow directions, both, and then flow can be singular or multi-pass. Okay, and fluid can pass over the heat transfer surface 1 or more times. So there's multiple types of heat exchangers. So this, and we'll talk briefly about these. A tube and tube, double pipe heat exchanger, shell and tube heat exchanger, spiral plate heat exchanger, and a bracelet for cryogenic services. So, and I'm moving fast on purpose. I'll slow down here in a minute. This will be up on YouTube, and I've got a YouTube channel, Carl Colmetz, CPE, Certified Practicing Engineer, which is part of the IECPE group, and so you'll be able to go back and watch it. And what happens in the next year, we'll have 1,000 views of the videos on YouTube. So we've got quite a few videos posted, and over about a 12-month period, we'll have over 1,000 views on YouTube. A double pipe heat exchanger looks like this. Okay, so the waste heat stream, the stream that has heat, and the heat's to be fluid, is kind of a counterfluent, and it flows in separate pipes. Double pipe heat exchangers are very good when you have high fouling, when you have slurries, when you have things like this. So they tend to look like this. The negative is they must be completely dismantled for inspection and cleaning. Heat recovery applications include those with a very viscous liquid and a liquid with particulate matter. When liquids are used, the propensable solids can be as high as 40%. A shell and tube really not designed high solids. So you might use a double pipe heat exchanger. And here's typically what most of the time we use. It's a shell and tube heat exchanger. We'll talk quite a bit about how to design one of these. We're going to talk about what the TEMA numbering system is actually by letters, and we'll talk about the steps to go through to design a heat exchanger. One fluid flows through the tubes, and the other fluid flows through the shell and over the tube funnel. The vapor flows through the shell while the liquid flows in the tubes. Removal of funnel makes the heat exchanger easier to clean, although the tubes themselves may be difficult to clean. This type of heat exchanger is often used for non-fouling services. Both the shelling tubes can be difficult to inspect. So there are certain types of heat exchangers that I don't recommend for fouling service. There are certain types of shell and tubes that you can pull and you can clean, and we'll talk about some of them. And we'll also talk about how to make it a little more fouling resistant in today's presentation. So they obviously kind of look like filters a little bit. So if you wish to have really a lot of solid particle content, you don't necessarily want to use a shell and tube heat exchanger. You might want to use a spiral heat exchanger. You might want to use a tube and tube heat exchanger. Most heat exchangers are shell and tube, and heating water with heat released by condensers and refrigeration systems, heat recovered from boiler blowdown systems. There's a whole group of shell and tube heat exchangers. This is probably the largest group would be shell and tube. The second largest group would probably be fed fans. Spiral heat exchangers look like this. The flow goes in a circle, and so flow goes in one side is counter current, and out the other side, the solids can accumulate along the bottom and move out. So they're kind of a self-cleaning, compact design. They're used in utilities a lot. They're used in where you have high solids. Okay, you can actually use a spiral heat exchanger. So basically what happens, the solids will fall to the bottom, and the flow will generally move the solids out of the heat exchanger. It's kind of got a self-cleaning kind of effect, particularly when the unit is horizontally bound. So all the particles will settle to the bottom, and automatically causes a velocity increase, which scrubs away any accumulation. So steam heating of slurries, heating of sewage, cooling, heating of processed pulp and paper mills, PVC slurries. So there's a whole group of things which have high solids, which you can use a spiral heat exchanger. And a lot of times they'll put them on top of a column. It can be sitting on the very top of the column, spiral heat exchanger. And then it's a combination overhead condenser and overhead receiver in one unit. So the vapor goes up, condenses, and it automatically refluxes back down the column. So there's a low pressure drop, spiral heat exchangers can be used on the top of a column. Condensing on the top of distillation extremity columns, vent condensing, reactor cooling condensing, surface condensing, and evaporation plates. Plate heat exchangers are plates that are stacked together. You might have one process on one set of plates, and the second process is on the second set of chains. And so they have a lot of surface area. Okay, and so we know that the heat transfer is Q equals UA delta T. And so when you have a lot of surface area, you have a lot of A, you get a lot of heat transfer. All right. These are typically used for cooling water systems. If a lot of times if you have seawater, you can bring seawater in from the sea. You'll put it through a plate heat exchanger like this. And then you'll put your cooling tower, not your cooling tower, your cooling water will be on the other side of the plates. So on, say, on the blue plates will be seawater. On the red plates might be cooling water. And so you will actually reject the heat out of your plant back into the ocean. And that happens at a lot of places where they actually reject heat back into the ocean. And so there's a lot. This is a common use for this plate type heat exchanger. So there's special metallurgies for seawater. Obviously, I'm going to need a high metallurgy because it's got a lot of salts. But this is typically, I'll see these in a lot of ethylene plants. Ethylene plant in Indonesia has a large bank of these, and they cool their plant against seawater. And so that's in Indonesia. Plate heat exchangers, because they're got a lot of surface area. They can be more efficient than a shell and tube. Low investment costs, operating costs, low fouling. So they're a good choice. So you've got a double pipe, you got spiral, you got shell and tube, you got plate heat exchangers, and then you got welded plate heat exchangers. So now these are typically for cryogenic services, and so they're welded together. They can't be opened up, so there must be very clean services. So you might do propylene refrigeration with ethane, and so they're typically, they look like this. They're typically welded together. They're very efficient. They have a lot of surface area, and so for air cryogenic applications, air separation, for natural gas plants, for ethylene, you'll see a lot of these plate fin exchangers. So they provide a very large surface area, right? And so they're only probably 10% equivalent for a shell and tube heat exchanger. So they're gonna have 90% more heat exchange. All right. The problem is, because they're welded and they're typically made of aluminum, which is a softer metal, there's been some catastrophic failures with fin exchangers due to commissioning errors. They're supposed to be started up with very small temperature changes, very low thermal stresses. It's a soft metal, they're welded together. And it's like it's kind of like a paper clip. If I flex it too many times, it's going to break. And if you start them up quickly and you flex the metals, they've actually opened up and let gas come out. And there's been some pretty catastrophic failures of plate exchangers. So you gotta baby them. You got to start them up with very small temperature changes and very low thermal stresses. So how do I want to design a heat exchanger? All right. So I want to develop a simple process flow diagram. Then I want to develop a P&ID. I want to do a process simulation. And then I want to develop a process data sheet. Okay, these first four are typical chemical engineering jobs. All right. And then I'm going to send that data sheet to someone who might run a program called HTRI for mechanical design. I've got a really good guy that does all my HTRI, met him in the US, and he's a specialist in that program. Process simulation, there's 4 or 5 major process simulation tools. And all process engineers might do 1 to 4. Mechanical engineer might do HTRI, and then you send HTRI to a vendor and you build a heat exchanger. Heat exchangers are not expensive. A heat exchanger might cost $50,000 US. Obviously, we think they're really expensive, but they're not. And so a normal size heat exchanger might be $50,000 US. What costs a lot of money is the foundation, the structures, the piping to and for it. Typically, the equipment cost is about 30%. The erection cost is around 60%. Okay, so that's just some rough numbers. And so we'll develop a process flow diagram. Just a block diagram, develop a P&ID, develop a simulation, develop a process data sheet. In developing the process data sheet, we use TEMA to decide what kind of heat exchanger we want it to be. And we'll talk about that. It's in the data sheet to HCRI. I'll show you some HCRI outfits. You send HCRI outputs. You send that to a vendor. He's going to fabricate it, and he's going to build a heat exchanger. A lot of vendors don't do 1 to 5. Okay, they only do 6 and 7. Okay, but so process engineers tend to do 1 to 4. Mechanical engineer will do 5, and 6 and 7 is typically done by a vendor. All right, so let's process flow diagram, simple block flow diagram. Here's a project that we done for This was actually done in Thailand. So this is a simulation we ran, and this was for a project we done in diagram. Simple block flow diagram. I've got a feed drum, I got a pump, I got a heat exchanger, I come into a small distillation column, and then the bottom goes out and goes back through that heat exchanger and goes to storage. And here's your heat material balance. Sometimes I'll build the heat material balance in Excel. Sometimes I'll build it in process simulation. If it's real simple, you can just do it straight in process simulation. If it's more complex, sometimes I'll build it in Excel. And here's a simple PNID, and this is that PNID of that very first drum. I come in, I got a drum, I show the levels, I show the level bridles, I show the makeup gas, I show the vent to the flare. And so typically, then we'll build the first PNID in Excel, sometimes in AutoCAD. It's easier to build it sometimes in Excel. Once you've built these blocks in Excel, you just pull them in. And so sometimes we'll build them in Excel. Develop a simulation. All right, so if you're going to simulate a heat exchanger, sometimes they'll simulate fast. Sometimes you can spend 2 or 3 days trying to simulate a heat exchanger, which is kind of amazing. And so, so I've done a lot of simulations over the years, and some people ask me, okay, what am I doing wrong here? Some guy will call me up. He's tried to run a heat exchanger for 3 days now, and you can't get it to converge. And so I've got kind of the rules of how to develop a simulation. Specify only 3 of the 4 streams. Don't specify the temperatures of all 4 streams. You got to have one of them with the ability to float. Typically, I only specify the inlet temperatures. All right. Okay. So I specify the 2 inlet temperatures. I specify the area. And you change the area until you get a reasonable outlet temperature. We'll talk about what a reasonable outlet temperature is next. Specify the heat coefficient. And then I specify the pressure drop. Okay. So I only specify 2 streams. I specify the area, I specify the heat coefficient, and then I specify the pressure drop. In the field, the pressure drop is 5 pounds, 0.3, 0.4 bar. And I'll show you some data sheets where I think we specified 0.4 bar. So if you do this, simulation will simulate in seconds. Don't over specify the temperatures, specify the area, specify the heat coefficient, and do the pressure drop. And it'll converge fast. If you try to over specify too many streams, if you don't specify the pressure drop, sometimes it doesn't converge at all. So this would be kind of simple steps. I got a whole course I teach on how to make simulations work. But this is how I'm going to simulate a heat exchanger. Don't over specify the temperatures, specify the area, specify the heat transfer coefficient, specify the pressure drop, and it'll simulate in 3 seconds. It'll close fast. Now this is out of the handbook. So what are some reasonable approach temperatures? All right, for shell and tube, maybe 10 degrees C, 15 degrees F, 10 degrees C. The problem is if you got too close an approach temperature, the heat exchanger gets very large. All right, so you've got to trade off between energy recovery and the cost of the capital. All right, so shell and tube, maybe 10 degrees C, double pipes are a little better. Fin fans, maybe 15 degrees C, plate fins 3, because remember you got a lot more surface area in a plate fin, a spiral, you got a lot more surface areas, you get within 3 degrees. Recuperative exchangers, like on a cogen, very large heat exchange transfers, maybe 30 degrees. And so what you want to try to do is get a reasonable number for minimum temperature approach so the heat exchanger doesn't get too large. And so what is a large heat exchanger? Well, a large heat exchanger is we limit it by what we can ship. All right. And so instead of having the one very large heat exchanger, we might have 2. So we can ship up to 3 meters pretty easy. and we can ship up to 12 to 15 meters long pretty easy. So if it's a much over 3 meters or much over 15 meters, it's hard to ship. So we'll actually break it into 2 heat exchangers and maybe ship a 2 meter by 12 meter, 2 meters by 12 meter heat exchangers, because shipping breaks into the how we design heat exchangers. Okay, so you got to think about shipping and shipping costs. And so you might actually build 2 smaller heat exchangers and make it easy to ship. This is right out of the handbook. These are guidelines for minimum temperature approach. This is out of the handbook. This is U values. So if you're doing water in 100 psi gas, 100, this might be the U value. Condensing with water, here's some different ones. MEA 120, 1000 psi gas, 1000 psi gas, steam, reboilers, hot oils, heat transfer fluids, reboilers. So here's some typical U values. All right, so you're going to pick 2 of the temperatures. You're not going to overspecify the temperatures. You're going to guess what an area is. You're going to put the U in. You're going to put the pressure drop in. You're going to converge it. If the temperature approach is good, that's a good area. If the temperature approach is high or low, you might have to add some more. You might have to add some more area to get your temperature approach down to 10 degrees. So that's kind of how you develop a simulation. And here's some more. This is out of the handbook too. Here's some more U heat transfers and fouling resistances. And so you build a simulation. And here's a converged simulation. Out of that, this was that one I showed you, the one I previously showed you, and it's got heat duties. It's got a UA is there. It's here's the feeds, and here's the hot side condition. Here's the cold side condition. So this was the previous, the same previous one that I just showed you for Thailand, where we built that unit in Thailand. If you develop a simulation, here's a simulation output. So now you go develop a process data sheet. All right. So we've done a simple PFD. We've simulated it. We've got reasonable outlet temperatures. We've got the simulation outputs. We know the U, the A, and the fouling factors. There's a group of fouling factors that we put in the handbook. And then we got the type of heat exchangers, which we have TEMA specifications for, and then we put in safety factors. We'll talk about safety factors because for heat exchangers in particular, high safety factors are not a good thing. And we'll talk about that later on in this presentation. All right, so we got to develop a data sheet. So we take the simulation outputs. We got to list the U, the A, fouling factors, the type of heat exchanger we want, and then we got to put some safety factors in. All right, and here is that data sheet. All right, so we're going to have to put my glasses on so you can see it better. All right, so basically this is this same heat exchanger that we're talking about, and it's in Rayong, Thailand. And there's the fluid flows, there's the operating temperatures, there is the thermal conductivity, the viscosity, the specific heats, the density. All of these come straight out of the simulation. Allowable pressure drop is 0.4. Okay. From this construction of one shell down here is the mechanical design. From this point up is the process design. So the process guy fills this top half in, the mechanical guy fills this bottom half in. All right. So I'm going to send it off I'm going to send this top data off to somebody to run HTRI, and he's going to fill out this bottom section. Okay. He's going to fill out the design temperature. Sometimes I'll put the design temperatures in, the number of tubes, the length, the tube shell type. He's going to answer all of these questions here in HDRI. So we're going to fill out this top half. Now, what the Coleman's handbook helps you do is to build this process data sheet from the process engineering point of view. So for a pump, it teaches you how to fill out the top half of this for a pump. For a heat exchanger, it teaches you how to fill out the top half of this for a heat exchanger. For a distillation column, it teaches you how to do this. So that's what the purpose of the Coleman's handbook is to fill out the top half of this data sheet. Okay? And that's going to be one of your deliverables as a process engineer. Develop this data sheet. And the process engineer's got to fill out the top half. Mechanical engineer's got to fill out the bottom half. So, and we use TEMA to decide what the heat exchanger looks like. And we give it letters, A, B, C, D, for each part. So the front half, what we want the shell to look like, and what we want the back end to look like. Letters are given for the front end, the shell, the rear end types. An exchanger is given a 3-letter designation. Okay, and this, everybody uses TEMA. And so for low pressure and a low pressure, this is called a dollar head. And it's low pressure. For cooling water, I might use something like this. For most hydrocarbons, I'm going to use a B because you got bolts here. You've got what's called this dollar plate. You got a lot more area for leaks. I've got these bolts here that bolt onto the shell. So typically, if I've got a hydrocarbon or higher pressure, I'm going to use a B. I'm not going to use an A. A is for standard dirty tubes where you have to take this plate off and clean it. B is for a little more clean side duties. Use it possible since it's cheap and simple. It's a little safer too. So in general, for hydrocarbons, I'm going to use a B. All right. For cooling water, I might use an A. For C, it's a removable shell for hazardous side materials, heavy bundles, or service. It means frequent shell cleanings. N is for fixed hazardous fluids on the shell type. D is for welded or tube sheet bonnets for high pressures over 150 bar. So they got A, B, C, N, and D types for the front end. Okay, so these are the front half of the heat exchanger. Then they got the middle section. All right. So they've got E, the most common. Typically, I tend to like an E. All right. So I'm going to use a B on the front end. I'm going to use an E on the second. It's most simple. It's common. It comes in and goes out. One pass shell. F shell is used when there's 2 passes and pure counterflow is needed. There's actually got a baffle along the middle. It needs to be very clean service to have a baffle. And so it comes in here and it goes out that way. We'll talk about these baffles. And I want to kind of be careful when I'm using baffles for fouling service. J, you've got 2 inlets and it comes this way. An X comes this way. You've got central fluid entry and exit, no baffle to use, very low pressure drop, used for vacuum condensers, low pressure condenser. So it just goes in the top and at the bottom. G shell and H shell are single double split flows. So they look like this. And so these are the types of the shells. I typically use that very first one, which is really simple. Okay. Bundle types, rear heads, U-tube configuration. The main objective is designing to accommodate thermal expansion that's allowed for easy cleaning. So I typically use the U-tube. All right. It allows for independent expansion of tubes in the shell. Only 1 tube sheet's needed on the very front. And even number of 2 passes in the tubes, except those in the outer row. So this is what I typically design. This is the front. It's got a U-tube. And it goes in the top and out the bottom. So this, for hydrocarbon service, this is what I design. 6 tube sheets. Got to be very clean surface. It allows mechanical cleaning of the inside of the tubes, but not the shell because it's welded to the tube sheets. It's low cost, limited thermal expansion. Individual tubes are replaceable. Pull through floating head. Occasionally, I'll use a pull through floating head. It's able to move with thermal expansion. Tube bundles can remove cleaning. Easy for cleaning. All right, and here's TEMA specifications. So we have A, B, C, N. We've got these, and we've got these. All right, so typically, I'm going to use a B, E, and an M for hydrocarbon service. So that's going to be my choice. Okay. For cooling water, I might use an A. For high pressure, I'm going to use down here. If I got a kit reboiler, I'm obviously going to use K. Okay, so there's different things that you're going to use. And what we did for the handbook, we actually colored it. So this is out of the handbook. We actually went in and drew it a little better. And this is out of the handbook. So I typically, for hydrocarbons, I'm going to use B, which is a little safer than this dollar plate. I'm going to use an E, and I'm going to use an M. Okay. There's a BES. So it's got a B on the front, and it's got a floating in the back. So you can pull it out. You can take this back end off, and you can clean. All right. When you pull it all the way out, you actually clean the outside of the shells. So I can take this back end off. I can clean the inside of the shells. After I pull it out, I can clean the outside of the tubes. All right. So this is an okay design. BES is okay. BEM is okay. So that's kind of that's typically what I use. All right. So 5, 6, and 7 are typically mechanical engineer. So I'm going to send the data sheet to HDRI for mechanical design, and then we send the HDRI output to the vendors, and they build the heat exchanger. All right, so what do they look like? Well, here's an HDRI. Okay, now this is one. This is one we built for Kuwait. All right, and here's the diameter is 2 meters and it's 6 meters long. BEM, imagine this. One of my heat exchangers is a BEM. It's horizontal. It's gross efficiency, and it's 36,000 meters cubes. So this is the shell. All right, here's the fluids. He's got all of this down here. He's got the number of tubes. He's got the tube ID. He's got the length. He's got the diameter. He's got the shell. He's got the metallurgy. He's got all of the things that a heat exchanger vendor is going to need to build this. And there also comes with a drawing of what the heat exchanger should look like. All right, so it's got a general arrangement drawing, and it's got, so process engineers, this all comes from us. And this all comes from mechanical engineer. All right. And so one of our deliverables as a process engineer on every job is to deliver this top half. All right. And here's another one. And this is, I think this is that same one, the very first one I showed you. Anyway, so we come here. It's a BEM. Imagine this. Imagine it being a BEM. For me, it's 250 shell. It's tube geometry. Tube length is 3.6. Pitch ratio, layout. Tube passes 2. Shell inlet. There's the nozzles. Thermal resistance, velocities, flow fractions. Okay, so this is the HDRI output. For this was, I think this was that very first one that I showed you that we did for tiling. Anyway, but this is so this is kind of how we want to do it. We do a simple PFD, we do a P&ID, we run a simulation, we build the top half of this data sheet. We pick the type of heat exchanger based on TEMA. And I typically, for hydrocarbons, I like BEM. For cooling water, I might use AEM, okay? Or AES. I'm okay with a E and a S. So that's typically what I tend to do. And here, I thought this was, okay, so basically, this looks like it's got a dollar plate, so it's an A. It looks like it's got an S over here, so this is an AES. Anyway, but I thought it was pretty neat. So the cooling water's coming in, it's going that way, the hydrocarbons are being cooled, it's coming that way, and it goes out. So I just thought that was a neat picture. But this is an AES. Okay. Here's a typical, this is out of the handbook. We drew this in the handbook, and there's a tube side in, tube side out, and tube sheet. So this is an M, and it's a B. Okay, so it's an E and an M. He's probably got doesn't have dollar plates. So anyway, here's one that's a fixed tube sheet. The problem with fixed tube sheets like this is I can't pull this out to clean these. So these need to be real clean service. Now I can acidize these in place, but I can't water wash them. I can't do much with them in place. So unless it's real clean service, like for a vacuum system, I might do something like this. That's got a really clean surface. Okay. This one I can pull. I can pull the bundles out, so I can take the back end off. I can take the front end off. I can clean these side, but it's going to be hard to clean the shell side. Reboiler looks like this. I pulled this picture out of the handbook. And here's a thermal siphon reboiler. Looks like this. Here's a horizontal reboiler. I like this because the liquid comes off the tray through the reboiler at least once. Where this one, the tray drops into here, and some of the liquid here may not necessarily go through the reboiler at least once. So I actually like this this configuration a little better because it comes. Sometimes I'll put a baffle right here, and then it's got to go through the reboiler at least once before it goes out the bottom's product. And so if you got a forced circulation, you might have a small pump here and turns it over pretty quickly. So that's a forced circulation type. Heat exchanger safety. Typically, only one side of the heat exchanger is rated for high pressure. If the heat exchanger is leaking, do not isolate the low pressure side. There have been examples where this dollar plate has blown off the front of the heat exchanger. All right, so be careful. A lot of times in HAZOPs now we'll put a relief valve on this low pressure side. Okay, all right. So there's what's called a 10/13 rule, which I really wish it was part of the code. It's not. It's just a rule. And the 10/13 rule says that if the tube's for 13 bar, the shell side should be rated for at least 10 bar. That's the 10/13 rule. If we don't rate it for at least 10 bar, you have to add a relief valve. And the code says if you don't rate it, you have to add a relief valve. Okay. The cost of rating it for 10 bar is very cheap. The cost of adding a relief valve and the piping is expensive. Okay. So in general, I always try to follow the 10/13 rule, where if the tube side's rated for 13 bar, the shell side's rated for 5 bar or for 10 bar. All right. So let's look at an example. If the tube side's rated for 13 bar and the shell side's rated for only 5 bar, and the rupture of the shell side is about 200%, if this 13 bar tube ruptures, I'm going to go into this 5-bar section, and I got the potential to rupture the shell because the shell's only rated for about 200%. If the tube is rated for 13 bar and I rupture the tube and it's 10 bar, I don't necessarily rupture the shell side. And so if it's 13 bar and the shell side's rated for 5 bar, if I rupture a tube, I can blow up the shell. If it's rated for 13 bar and the shell side's rated for 10 bar, I won't necessarily blow up the shell. Okay. And so I like this 10/13 rule because we only rate it for 200% of design. We design it for around 200%, and we do a hydro test to 120 or 130% of design. Okay. Now this is a rule. It's a rule I want to follow because I don't want to hear one day that one of my heat exchangers blew up because I didn't follow this 10/13 rule. And I'm already running out of time. Fouling heat exchangers, I'm going to go through this. I've got a typical heat exchanger designed with limited optimization. If you have a fouling heat exchanger, you need to design it better. So let's talk about this. Here's pictures of heat exchangers that might be in Malaysia. Okay. These are in Johor. And basically, this is the bottom half, the bottom 20% of this heat exchanger is fouled. Okay, that's a pretty ugly picture there. These pockets right here are all full of fouling materials. You're not going to get any heat transfer here. This is polybutadiene fouling, and this is cooling tower field, where the cooling tower kind of broke apart and plugged up the cooling water side of a heat exchanger. All right, so this heat exchanger's lost probably 20–30% of its surface area. This one's probably lost 30% of its surface area. This one's lost a lot of surface area. Obviously, this cooling water flow is not what it's wanted to be. So here's kind of how you don't design heat exchangers. And we do this all the time. We design them poorly for fouling services. All right, so how do we design them? Okay. We can design a heat exchanger with increased efficiency very easy. All right, so what do we want to do? So what we have here is we have these baffles, and we deliberately put these baffles in to make the flow go around the heat exchangers. And they're a good thing. Baffles are a good thing if they're done correctly. They're a bad thing if they're done incorrectly. All right. So there's all kinds of baffles you can use. This is out of the handbook. We talk about the different types of baffles you can use. Single segmented, double segmented, multiple segmented types of baffles. So what's a bad baffle? There's a disc and donut. There's all kinds of baffles. Well, if I have a fouling service and I'm going here and under and up and down and up and down, what happens right here? Okay, so I come in here, I go under, I go up. I have a dead zone right there, and I'm going to fill that whole section up with trash. If I put just small notches under this baffle, typically I want the flow to go down, okay, for fouling service. But if I'll put small notches underneath these baffles, okay, that trash won't fill up and it'll come and go out. Okay. So if I'm going to design a heat exchanger, I want to design it, if it's a clean service, this is fine. If it's kerosene, it doesn't foul, I'm okay with this. Go up and down and up and down. If it's naphtha, if it's gasoline, I'm okay. If it's heavy fouling service, I'm going to make them pictures like you just saw. I don't want to design them the same way I'm going to design a kerosene or a cooling whatever. So anyway, so what I need to do, I need to put little notches right here so that this will flow through. I need to put little notches. That baffle doesn't need to come all the way to the ground. I just need to put little notches. All that trash will move. All right. The reason the vendors don't put the notches is the notches make it a little less efficient. But after you've lost 20% of the efficiency, it's way less efficient. So it's a slightly less efficient with the notches when you first start it up, but you retain your efficiency over the life of the heat exchanger. All right, so if I'm going to design for fouling, I'm going to put small notches right here to have this flow so I don't fill it up with trash. Process design engineer puts about 20% safety in. Remember we talked about safety. A mechanical engineer is going to come behind me and add another 20%. So we may be running 140 to 140% of design flows. That's fine if I'm running the plant 120%. What happens if I'm running the plant at 80% of design? Well, if I'm running the plant at 80% of design, I can go into the laminar flow regime. All right. So laminar flow versus turbulent flow. This laminar flow, I'm going to have a layer of kerosene, of diesel, whatever you want to call it, right here. And it's going to be extra, heat transfer. All right. Because turbulent flow is going to be clean surface. Okay. So basically, if we're looking at if it's laminar flow, I've got this orange layer here, very poor heat transfer. If it's turbulent flow, I've got excellent heat transfer. All right. And so if I'm going to design for 144%, I need to be running at least 110%. If I know the plant's not going to run 110, 115%, I better design the heat exchanger for lower velocities. All right. And so if I have less flow, I can have 18% less heat duty and 12% less heat coefficient. And that makes sense to you. You can understand. If I break into that laminar flow, it's just going to fall off like you can't believe. Now, there's certain things you can do. All right. You can go run flow regimes. You can calculate the Reynolds number. And sometimes I've went out and plugged some of the tubes. Okay, they way over designed the heat exchanger. And I might plug 5 to 10% of the tubes, and the heat exchange actually goes up because the velocity goes up. There are inserts that you can put inside the tubes. They're little wires. And they're called inserts. They raise the pressure drop slightly. They raise the velocity slightly. Some are better than others. Some of the inserts I don't like. Some of the inserts I do like. You probably need to perform a study, determine the best path forward to increase the efficiency of the existing heat exchanger. So now if you're running a laminar flow, you reduce the number of tubes, you can add some inserts. So these are things that you can do. And then I've got a troubleshooting, which I'm just going to flip through. All right. So went on. Thanks to the university today for the opportunity to talk to you guys a little bit about KLM and ICPE. If you're a student and you want to write articles, I'm okay with publishing student articles in the magazine. In the next 20 years, it'll probably be good for your career if you have 20 published articles. You probably need to look at writing one a year. Building operational excellence, we talked about safety, we talked about cost, we talked about building up people, general heat exchanger design, PFD, PNID, run a process simulation, build a data sheet using TEMA, go build HTRI, designing for clean service. I'm happy. If I'm designing for fallow service, I want to put the notches in. If I'm running the laminar flow, I either want to put inserts in or I want to put notches in. So these are things I've got. If you got some questions, you can type them into the Q&A box. We'll try to answer them. And so the webinar is being recorded, and we'll try to answer we'll post it at some point on LinkedIn. One of the previous webinars, I didn't read out the questions. Now we can see the questions, but on the webinar, on the webinar you can't see them, so I'm gonna read these questions. Why will even distilled water cause fouling to heat exchangers? Water's one of the highest fouling things there is. It has high salts. It has even distilled water. It's going to have salts. It's going to have in a closed system, like in a cooling tower system, you're going to have all kinds of growth. You're going to have microbiological growth. So water is one of the highest fouling things, and you don't think of water as one of the highest fouling things. You spend about $1 million a year in a chemical plant trying to control cooling water with chemicals. So water is just a bad actor. Actually, kerosene or diesel or benzene or any number of things is much less fouling than water. So we think of fouling, we think of water as not fouling, but water is very fouling. How to apply for IECPE? Okay, so you go to the website and you can join. There's several things you can do. One, you can join for free. If you want to buy copies of the guidelines, we charge crazy prices to companies for the guidelines. We almost give them to the students for a small fee. And so you can join for free. You can buy the guidelines low cost. If you buy the guidelines low cost, you can get a certification. And so go to the website, www.iecpe.com, or send me an email. Okay, the next question is, what are the requirements when considering impingement baffles? What guidelines are there in designing impingement baffles? Okay, and what an impingement baffle is, if I know I've got two-phase flow, or if I know I've got solids, I don't want that solid to hit that tube, because I'll wear out that tube pretty quickly. So sometimes I'll put a baffle where the feed comes in, and it hits that baffle instead of the tubes. Typically, I'll just put it across that area of the tube where the feed is coming in. I probably can find some guidelines for impingement baffles, but they're just to protect that tube. So as the feed nozzle is coming in, typically it's coming in from the top. If I know I'm going to have solids, if I know I'm going to have two-phase flow, I'm just going to cover that set of tubes right there so that the tubes won't get ate up. Good questions. Dear Carl, can the temperature cross actually occur? What will be the impact of temperature cross the operability of the heat exchanger? Temperature crosses occur. They occur inside the heat exchanger, even though the inlets and outlet might not cross. Sometimes in the HTRI guy will tell me you got a temperature cross inside the heat exchanger. And what we do is we'll split it into two heat exchangers before it crosses. All right. So you can have a temperature cross, and if you do have a temperature cross somewhere in the heat exchanger, until it balances out, you get no heat exchange. So you're wasting tubes. So HCRI will come back to me and he said, well, I split this heat exchanger into two because you had a temperature cross. Very good question. Okay, so in the handbook, I've got pictures of what counterflow temperature should look like and crossflow temperature should look like. But you can have a temperature cross, and the HDRI guy will come back to you and say, even though your four outside are not crossing, it's an internal cross. We're going to split the heat exchanger into two heat exchangers. So we've done that. HDRI will tell you that. There's only one session, or there will be more sessions? Typically, I try to do a session like this about once a month. I post it on LinkedIn. If you go back to my YouTube channel, you can see I'm trying to do one of these about once a month is what I'm trying to do. All right, Mr. Carl, thank you for your presentation. About the heat exchanger safety 1013th rule, may I know if a tube is rated for 13 bar, the shell side is rated for 10 bar. That's 11 bar. The rupture shell is 200%. Will the shell rupture? No. Now, okay, so think about this. The 1013th rule. Okay, so imagine the rupture is 200%. All right, so if the 13 bar on one side, if it's 11 bar on the other side, the 200% is 22 bar. It will not rupture. If it's 5 bar and it's 200%, it's 10 bar, so it will rupture. I'm unhappy the 1013th rule is not part of the code. Okay, I really wish it was. The code says if you don't follow the 1013th rule, you have to put a large heat exchanger. I'm sorry, a large relief valve in. Okay, but I really wish the 1013th rule was part of the code. All right. Next one. Hello, sir. How designing simple heat exchangers from condensing design? Okay, a simple heat exchanger typically is liquid, and you don't have to worry about change of phase. Particularly if you have change of phase in water, if you have change of phase in a lot of hydrocarbons, you have that first drop of liquid can be very acidic. So you have to worry about corrosion and damage to the tubes wherever that first drop of liquid is made. So it's important. You might have to have better metallurgy. You might have to have a lot of people will put a water wash, like you're in a crude column. You might put a water wash in front of that fin fan for that condenser design. Excellent question. Which flow is good to increase the efficiency of the heat exchanger, laminar or turbulent? If the baffles created turbulent flow. Okay, so baffles will create some turbulent flow. Okay. I'm really thinking more turbulent flow inside the tubes than I'm thinking in the shell side. The baffles will create some turbulent flow on the shell sides, where I'm worried about laminar flow is in the tube side. Okay, good question. May I know how to make decisions on changing the heat transfer medium? Okay, so there's been multiple cases where I've gone up in the heat transfer medium and my heat exchangers actually got worse. All right, so you need to run a simulation. You need to, so you might be running 50-pound steam. I go up to 100-pound steam and the heat transfer actually got worse because there's different types of boiling mechanisms. And if you get into the wrong type of boiling mechanisms, the heat transfer can actually get worse. So that's a very complex question. May I know how to make the decision on choosing heat transfer medium? Andrew Slowly, a friend of mine, has a really good article on this where he talks about they raised the heat transfer coefficient, they raised the heat transfer medium, and the heat transfer actually went down in the system. So it's not straightforward. It's more complex than you think, just to change the heat transfer medium. Tell us the difference between heat exchanger design and rating. Tell us the difference between heat exchanger design and rating. Okay, so heat exchanger design is my normal operating design. All right, and so I want to know, say if I'm running 10 bar, okay, I want to, my normal operation is 10 bar. I don't want to design, I don't want to rate it for 10 bar. I want 20 to 30 to 40% safety. All right, so if it's going to run 10 bar, I might design the system for 15 bar, and that's the rating. All right, so I want some safety there because if the pressure gets high, I don't want it to rupture. So heat exchanger design might be 10 bar, and then I'm going to rate it for 15 bar. So I got 5 bar safety. Is TEMA the only designing for shell and tube exchangers? No, TEMA has some stuff for, I think they have some stuff for fin fans, and they have some stuff for other stuff. I was just using the shell and tube, but I think they actually have some other ratings also. May I know the average life cycle for a piece of the heat exchanger? Okay, so typically we try to design chemical plants for 20 years. Okay. And so I would say an average well-designed heat exchanger might last 20 years. If you're a fouling service, if it's high corrosive systems, if it's uh, if it's if so they might not last 20 years. But an average cooling water system that's not real corrosive, I would say 20 years. Are you doing certificates? Well, yes, ICPE will give you a certificate, and if you go join ICPE, you study 5 of the guidelines, we'll give you a certified practicing engineer certificate. And so it's hard for the students to grasp how important this is to get when they go out in the field and they start trying to do things. They come back and they'll come back to me and they say, okay, I want to get the certification because I need to know how to do data sheets. I need to know some of this stuff that's in the handbook. When simulating for running exchangers, you have to calculate fouling factor for one side, change it while the fouling factor keeping constant. It's not an efficient way to calculate actual fouling. Do you suggest any better way? Yes. Send me an email. And I thought about covering this in this presentation. When I spoke to UPM 3 or 4 years ago, I talked about how to calculate fouling factors. So you take MCP delta T, Q equals UM, and you take the 2 formulas. Q is the same. One is a flow and one of them is a fouling factor. And you can actually break out and solve for the fouling factor on every heat exchanger. So when simulating for running heat exchangers, we have to calculate the fouling factor on one side by changing it, while the other side fouling factor gave me constant. Is there a more efficient way to calculate actual fouling? Can you suggest it? So what I've always done in a heat exchange, I've actually run it in Excel, and I put Q equals MCP delta T and Q equals UA delta T, and you solve for the U. All right, you can do it in Excel. You can solve for the overall fouling of that heat exchanger. Okay, and once you have them clean, and you might do one, you go get the data once a month, and you can see which ones are falling off, and you know which ones to change. I was a young engineer in the 90s in refinery in Houston. And that was my job. Once a month, I had to go rate the heat exchangers and write a report which ones needed cleaning. Okay. And it's simple in Excel. What is the pressure drop considered reliable in the industry? That's a question. I typically design for 5 pounds or 0.3 bar. Okay. If you need less pressure drop, you can for a vacuum service, which has really low pressure drop. I'll make the heat exchanger larger. But just for standard normal, pressure drop is about 5 pounds. How to define the water quality we need to pass through a heat exchanger? Quantity of water we need to pass through the heat exchanger. Okay, so basically, I'm going to put in the U. Okay, so I'm going to put in the U. I'm going to put in the inlet temperatures, the UA, and the flows of the hydrocarbon. And then the simulation will then define the quality of water that we need on the heat exchanger side. All right. And so I'll raise the area up till I get a reasonable delta T on the water. And then as I raise the area, the quality of the water will come down in the simulation. Okay, so I actually define the quantity of the water to pass through the heat exchanger in the simulation. That's the way I'm going to do it. What's your experience with ultrasound devices attached to the tube sheet to minimize fouling? That's an excellent question. When you do this UA delta T and you don't have a water flow, you actually have to use ultrasound devices on the water to calculate that water flow. Your heat exchanger vendor needs to come out, and he should do it for free. And he should put an ultrasound device on every cooling water flow that you have for your heat exchangers, and to tell you how much flow is there. If you don't have enough flow on your heat exchange, you're going to run into laminar flow. You run into laminar flow, you're going to have 10 times the fouling that you're going to have with turbulent flow. Okay, and so basically, I would have my heat exchanger vendor come out, do ultrasound devices on all of my cooling waters to minimize fouling. Excellent question. How can we maintain the efficiency of the heat exchanger? Keep the velocities higher. Add inserts. Okay. On the cooling water side, you can do what's called a backwash. And so there's several things you can do about it. Typically, they're designed to clean once every 5 years. And so we try to do, we just try to keep it okay. You're going to lose some over the 5 years. And if it's a really bad fouling heat exchanger, you'll put a bypass in and block it in online, take it off and clean it. How do you clean a double pipe heat exchanger? The outer pipe is typically welded. Chemical cleaning is the option. Do you replace them? You don't have to weld the outlet pipe. You can flange them. All right. So if they are welded, you're going to have to do a chemical cleaning. If you flange them, you can actually do a work wash. All right. And they are relatively cheap. So on a double pipe heat exchanger, if you have to, you can just replace them. Good question. What are the pros and cons of different types of heat exchangers? Shell and tube, plate, fan tube heat exchangers. Okay. Shell and tube is basically the industry standard. Plate, because they're close, thin sheets, they're going to foul more. A fin tube, typically I'll use a fin tube on fin fans. Okay. And so I'll use fin tubes up on fin fans. So typically shell and tubes are the standards. Plates are for clean services. The spiral heat exchangers for a little dirtier. Fin tubes I'll typically use on fin fans. Is this session being recorded? Yes, this session is being recorded. And I'm going to at some point I'll edit it and then I'll put it up on YouTube. My name is Lee. May I ask if fouling occurs as shown you in the slide, it's possible to restore the heat exchange by cleaning or maintenance to be used, or we should design a new heat exchanger. The pictures that I showed, you can clean them, put them back in service, but they're going to foul again. If you put the notches in, which you could do easily, you'll get more heat exchange in the life of the heat exchanger. You don't have to buy a new heat exchanger. You can just clean them. But obviously the heat exchanger that foul has very low efficiency. In the condenser design, once we take baffle spatial equal to diameter in condensing design, why should we take baffle spatial equal to the diameter of the shell? Okay, I don't like to do equal to the diameter of the shell. The most I would like to do is probably 60%. And it's basically to make the vapor flow across the tubes. Okay. And the HCRI guy kind of looks at this. HCRI guy also looks at vibration. All right. So if you don't put the baffles in correctly, they'll vibrate. And so HCRI looks at baffle placement, looks at baffle vibrations. HCRI has a really good program. All right. What for the pressure test, how much will be suggested? Either operating 1.5 or just follow specification. Okay, so basically you have what's called the design pressure, the rating pressure. And typically you want to go 130% of the design pressure for the pressure test. Okay. Now remember, it's designed up to 200%. Okay. And so we want to do a pressure test at 130%. All right. Now remember your relief valves. When you're designing relief valves will let you go up to 121% of the pressure. All right. So we test the heat exchanger up to 130, and the relief valve goes up to 121. All right. So typically that's how much you pressure test. Okay. In the guideline, when I talk about in the handbook, when I talk about relief valves, I talk about that you can go up to 121% test pressure. What is the major challenge of heat exchangers faced in the grill industry? How team has worked to tackle these issues? To me, the major challenge is the life, corrosion issues, is this fouling. Okay. And I'm not sure. I'd have to go do some research how TEMA has worked. TEMA is the naming configuration. I would have to go do some research to see how TEMA has worked to tackle this. May I ask something out of topic? May I know the common pressure difference in pipe with equipment that would set the product to significant energy flow smoothly for gases? Typically, if I'm going to size piping, I'm going to size for velocity. Okay. So the velocity is the same as pressure drop. Okay. And so for liquids, I'm going to go so many meters per second. For gases, I'm going to go so many meters per second as a maximum. And that's also actually a pressure drop. In the Coleman's handbook, we talk about what are the we've got a line sizing. That was actually the very first one we wrote, how to size lines. And we talk about what should be a liquid. You've got even a lower one for a pump suction. For pump suction, I want 3 feet per second. For just general lines, for liquid lines, I want 10 feet per second. For gases, I can go up to 30 feet per second. So there's some rough numbers. And so that feet per second will go back to pressure drop. Okay, so I actually size limits by pressure. It's the same pressure drop. And we look at pressure drop per 100 feet. It's the same as the velocity. Okay, but that's a good question. Okay. In terms of choosing cooling, is there any suitable refrigerant that can choose for process stream at huge temperatures such as 800 to 1,000 degrees? Okay, so typically what I try to do is I try to, if it's an 800 to 1,000 degrees, I don't want to cool that. I want to put that amount of heat back in the process somewhere. Okay. So if I've got a very huge temperature of 800 degrees, I want to put at least 600 of that degrees back into the process itself. So I want to get it down to 300 to 400 degrees before I start cooling with cooling water or doing some refrigerant. Because that's money. Okay. That 800 to 1,000 degrees C is money. I want to make steam. I want to put it back into the process. I want to do something with that high value heat. Okay, so I can make steam. I can put it back in the process till I get it down to 200 to 300 degrees, and then I want to cool it at that. Okay, good question. While safety design exchangers, what is a good population over design percentage for fouling? Basically, you put a fouling factor in there. All right, and so there's fouling factors. You might put 10% in if you know it's going to foul, and it's called the fouling factor. And it's in the handbook, what typical fouling factors you might want to use. Can you brief impingement plate in the spacing? It's important. So the impingement plate is a piece of metal that's put on top of the bundle where the gas or liquid's going to come in. And the impingement plate's goal is to stop from damaging the tubes right at the inlet. So you'll put a baffle over that set of tubes. If you've got solids, if you've got two-phase flow, you might put an impingement plate over the top, right where the feed inlet comes into the heat exchanger. Typically, I like to bring it in the top of the heat exchanger. So right that area where the liquid or gas might come in, I'll put a small impingement plate over the top of the tubes. I think that's all the questions we have. Excellent questions. Thanks for your time today. And
Okay.
yes, ma'am.
Okay. I think that's all for today. Ladies and gentlemen. Okay. Carl, are you still here?
Yes, ma'am.
All right. Okay. Okay. I just want to have a closing speech for you to
Yes, please.
express our deepest gratitude to Mr. Carl Gomez here for enlightening us with his vast knowledge and expertise and share with us about the design of a heat exchanger from A until B until to Z, not until to B until to Z, until all the knowledge that we want to know how to design according to TIMA's specification. We hope that Mr. Carl Gomez has really considered to join us as a speaker again in future.
Yes,
And
ma'am.
also hope that his insight and his guidance are very, because it's very valuable to us, and to me as well.
Thank you.
Okay.
Thank you.
We wish you, Mr. Carl, continue success in future. And thank you for your invaluable contributions during this session. All
Thank you,
right.
ma'am. All right.
Thank you very much.
Thanks for inviting me, and hopefully we gave you some gray hair today.
Thank you. Thank you a lot.
Thank you, ma'am.